So welcome to class number 17 of transport phenomena in mesoscopic and nanoscopic systems, and last day we were mainly talking about basis transformation, and we discussed that a wave function psi of r can be expressed in terms of different basis sets. So if phi old is a basis set, then the transformation from an old basis set to a new basis set can be given in terms of a transformation matrix C, and so this is a basis set, and this is also a basis set, and the expectation is that the basis sets are basically orthogonal, and the basis sets are also normal. Okay, so the basis set is basically orthonormal. Okay, so psi r can be expressed in either of the two basis sets, so we can write it as summation over m am phi old m, where phi old m is basically the mth component of this basis set. Okay, and this can also be written as summation over I bi phi nu I. Phi nu I is again the ith component of this basis set phi nu. Okay, and the relation between this A and B is again given in terms of the transformation matrix C as A1 A2 AM equals the matrix C times B1 B2 Bi. So this we saw last day. Of course have this relation that C dagger C is equal to the identity matrix, where this C dagger is the complex conjugate transpose of the matrix C, and this is equal to C dagger. Okay, now the third thing which I want to prove here is that although the operator representation might change as you go from one basis to another, and that is why we have this kind of relation that the new operator in the new set basis set is equal to C dagger times the old operator times C. The form of the operator actually doesn't change when you go from one basis set to another. Okay, so what I mean by form is that each operator might be a function of something. For example, let us say that an operator A old is basically written as exponential of the let us say Hamiltonian operator. So I am just giving an example here. Okay, so you might have seen what this exponential of an operator or exponential of a matrix here means. So exponential of an operator is the same thing as the exponential of a number. So exponential of this operator H is basically the identity matrix plus the operator H plus H square by 2 factorial plus the matrix H cube divided by 3 factorial and etc. So what we want to show here is that the relation between this operator or the form of this operator A old does not change as we shift to the new basis set. So let me write it old here. So because the Hamiltonian representation also changes as we go from one basis set to another. So if A old is given by exponential of this old Hamiltonian, then this implies that in the new basis set, the new operator for the same purpose, let us say it can be the momentum operator or it can be any other operator. Okay, so the new operator for the same observable is again given by exponential of the Hamiltonian, but now this Hamiltonian is basically represented in the new basis. So the relation between the operators does not change as we move from one basis set to another, and it is not difficult to prove. Of course, it is difficult to prove in a general way, but I will give you some examples and show that it doesn't actually change. So let us take this example that we discussed. So our old operator is exponential of this old Hamiltonian operator. So this new operator is just the so let us write it as A new is equal to C dagger A old. This is actually a matrix C. Now this is equal to C dagger. Now I am breaking this operator A old in terms of this exponential over here. So I C plus C dagger A old C plus C dagger A old C. So this is basically the square of the operator A old, and we have a 1/2 factorial over here plus other terms. Now note that this is equal to the identity matrix because we have this C dagger C is equal to C dagger. This is equal to the identity operator. Okay, so this is the total is equal to the identity operator over here. So this is equal to the identity operator 1. This is basically equal to A new. Now to get the form of this operator, we basically introduce this C dagger over here, because this term is basically equal to the identity matrix. So if we introduce the identity matrix in this portion, then it changes nothing basically. Okay, so we basically write it like that. So A plus 1/2 factorial C dagger A old C dagger A old C. So now this is equal to A new, and this is also equal to A new. Okay, so we have the identity operator I plus A new plus A new square by 2 factorial and up to infinity. So this is equal to sorry, it should be H actually, not A. So this is equal to exponential of the new Hamiltonian. So the relation between two operators in this case basically remain the same. So although the form or the format of the operator might change as we go from one basis set to another, but the relation between two operators actually does not change. So we can basically show it for a couple of other examples. So this was an exponential example which was slightly complicated, but there are other simple cases. For example, if the operator a old is equal to a1 old plus a2 old. Okay, so this is the sum of two operators. So in the new basis set, so this is the operator a in the old basis set, a1 is another operator in the old basis set, and a2 is another operator in the old basis set. And this a in operator is given by the sum of these two operators. So now a new is basically C dagger a old C, which is equal to C dagger a1 old C plus C dagger a2 old C. So this is equal to a1 new plus a2 new. So if an operator is represented by the sum of two operators, then also the relation between these three operators does not change. The operator in the new basis is still represented as the sum of those two operators, but in the new basis. So now let us consider an operator A, which is the product of two operators. So A1 old, A2 old. Okay, so now we can put third brackets here if we denote matrix. Anyway, so in the new basis set, this operator A new is again C dagger A old C. So I just break down this A old here and write it as C dagger A1 old A2 old C. Now to proceed from here, I basically introduce this C dagger here, and again this total is equal to the identity matrix, so it changes basically nothing if we introduce the identity matrix here. Okay, so let's proceed. So this is equal to C dagger A1 old C dagger A2 old C. So this is equal to A1 new, and this part is equal to A2 new. So this is equal to then A1 new times A2 new. So again, the relation between two operators does not change if we go from one basis set to another. So the relation between operators does not change when we go from one basis set to another. Although it is a fact that the representation of the operators might change, or the elements of the operators might change. Okay, for example, the rows and columns of the operator, those things can change, but the relation between two operators does not change when we go from one basis set to another. So now let us define something which is known as local density of states, and this is very important when we consider transport through nano devices. Now what is local density of states? So let us first define what is density of states. So density of states means the number of states per unit volume in case of 3D material per unit energy. Okay, so density of states is basically the number of states per unit volume per unit energy. Now the question is that is it actually sufficient to know only the density of states? So let me give you a simple example. Let us consider the case of a MOSFET. Okay, so as you know that the MOSFET has an N plus, let us consider an N channel MOSFET. So N plus source, I will label it as S, and then N plus drain, which I label as D, and then there is this body which is kind of P type. So let me draw the surface over here. So this is the surface, and on the top of the surface there is the oxide, and after the oxide there is this gate. Again, the oxide is not present all along, so yeah, and then this is the N plus drain, and this is the N plus source. Okay, and this is our P type body. So we have again contacts around here, but those things are not important, and I will not go into the details of those things. The reason why I am discussing is to understand the importance of the local density of states. So if we consider the Venn diagram, the spatial Venn diagram of this kind of structure, as we move from this source into the body and then into the drain. So what would the Venn diagram look like? So it would basically look somewhat like this. Okay, so the P type, in the P type the conduction band is higher. So let us consider that if this is in equilibrium and if no current is flowing, then the Fermi energy would be constant throughout this device. So this is the Fermi energy, let us say EF. Okay, and this is basically our this thing is basically our conduction band H. Okay, now if I ask you the question that does this device have density of state at an energy E dash, where E dash is, let us say, this much energy. This is considered the energy axis. So at this energy E dash, does this device have density of states? The answer is yes, because there are states in the N plus source and in the N plus drain. So this is our conduction band H, and E dash is above this conduction band H. So E dash is above the conduction band H in the source and in the drain. So there are states at energy E dash here in the drain, and there are states at energy E dash here in the source. Okay, so there are states here and here, but there are no states in this region. Okay, because this is P type, and here the conduction band H is higher than the energy E dash. Okay, now if I ask you the question that does this device contain viable or valid states at energy E dash, the answer is yes. So the states mainly reside here and here. Now the second question, if I ask you, would the states at energy E dash carry current through the device? The answer is of course no, because at energy E dash there is no state here. Okay, so because there are no state here, these electrons cannot flow through this barrier over here, provided that the barrier is thick or wide. Okay, so when I ask that does this device contain density of state at energy E dash, the answer is definitely yes, but still this answer is not sufficient to understand whether the current flow would occur through the device or not. So to understand whether current flow would occur through the device or not, it is actually important to understand this parameter which is known as the local density of states. So local density of states is nothing but it defines the density of states that is available locally. Okay, so if I ask you now the question that at this energy E dash, if local density of states is available at some point inside the drain, the answer is yes. So at all these points there are states available. Now if I ask you the question whether the local density of states are there inside the source, the answer is yes. So they are available somewhere here. Now is a local density of states is available inside the body or beneath the surface? So the answer is no, because no state at energy E is available at all these points, at this point, this point, this point, this point, etc. So local density of states basically, as the term says, it gives you the density of state at a local point. Okay, it does not define the density of state throughout your entire device, but it gives you the density of state at a local point. Okay, for example, at this point over here, at this spatial point over here, local density of states is available at energy E dash, but at this point over here, local density of state is not available at energy E dash. Then at this point, again the local density of state is available, but the local density of state is less than the local density of state at this point. So local density of state gives you the relative weight, or how much of that state at that energy is basically present at a local point. Okay, so I hope it is clear to you. And to understand whether the current would flow through a device or not, it is important to understand that how much of that density of state at a given energy is present at each point inside the device, and that is when the concept of local density of state comes into picture. Now just like this density of states is a function of energy, the local density of states this is basically a function of both space and energy. Okay, so this is written as density of states as a function of energy, and this is basically written as local density of states as a function of R and energy. R is basically the space term. Okay, so with this, let us go back to where we left off in class number 15. So we had this contact, and we had this device. So device basically means the channel, and then this contact has an isolated Hamiltonian HR. So if this contact is isolated from the device channel, this would have a Hamiltonian HR, and if this channel is isolated from the contact, this would have its own Hamiltonian H. So H is the Hamiltonian of the isolated channel. So remember that this is the Hamiltonian of the isolated channel, very important. HR is the Hamiltonian of the isolated contact, and then this channel and contact are basically coupled by this coupling operator, which we call it as tau. Okay, and we have been having this equation EI minus HR plus I eta, where eta is a small number, not number, it's a identity matrix multiplied by a small number. So eta is basically 0 plus IR. So where 0 plus is a very infinitesimally small quantity. Okay, so I eta minus tau dagger yr plus x psi equals to SR. Okay, so this first row is the equation for the wave function inside the contact, and the wave function inside the contact is basically coupled to the wave function inside the channel by this matrix tau dagger. So this is a matrix basically. Okay, this is also a matrix. Okay, and then for the channel we have this tau, and here we have E I minus H. Now H is the Hamiltonian for the isolated channel, HR is the Hamiltonian for the isolated contact, phi r is basically the wave function inside the contact when the contact is isolated. Okay, and so let me write it here. Wave function inside the contact when the contact is isolated, and this x over here denotes the wave function or the perturbation or the modification in wave function due to coupling with the channel. Okay, so the channel wave function should spill inside the contact, and this part or this modification due to the presence of channel, the modification in the contact wave function due to the presence of the channel is denoted by this part x. And why do you split this total wave function inside the contact in two parts, one for the isolated channel and one as a perturbation due to coupling, one for the isolated contact, so why do you split the wave function in these two parts, one for this isolated contact and one as a perturbation due to coupling with the channel? Is because it is easier to actually proceed with the formulation if we split these two things up. Okay, because this phi r is the well known part of the contact wave function. Okay, we can push this channel apart and then we can calculate the contact wave function. So this phi r is basically well known, but this x is basically not a well known quantity. Okay, so we are splitting the total contact wave function into a known quantity and an unknown quantity. Okay, and this is equal to 0 basically, and I repeat again that this I eta over here basically denotes a very small rate of extraction of electrons from the contact, and it would gradually become clear, but right now just know that this I eta over here indicates that electron in the contact can leak into the channel at a very low rate or can leak out of the contact at a very low rate, and this SR basically denotes reinjection of electrons into the contact, and this reinjection is necessary to maintain constant electrochemical potential or Fermi level inside the contact, because the electrons are leaking out of the contact through this part I eta. So electrons must also be reinjected inside the contact to maintain the constant equilibrium or constant electrochemical potential inside the contact. Okay, I would not say that to maintain constant equilibrium, but to maintain a constant quasi-equilibrium condition inside the contact, this reinjection of electrons by this term SR is basically necessary. Okay, and from here we basically arrived at this equation after some derivation. EI minus h minus sigma psi is equal to s, where s is given by tau phi r and sigma is given by tau gr, tau. So these are all matrices, so let me write it in that notation. Gr tau dagger, where Gr is equal to EIR. E is basically a number, it is a variable which denotes energy, minus HR plus I eta inverse, and this is known as the Green's function for the isolated contact. And from here we can write this equation for psi as psi equal to EI minus H minus sigma inverse S, which is equal to GS, where this G is equal to EI minus H minus sigma inverse, and this is known as the Green's function for the channel. So let me add a new page. So G is equal to EI minus H minus sigma inverse. This is known as the Green's function for the channel. Now note that this is not the Green's function for the isolated channel. On the other hand, this is the Green's function for the isolated contact, and one way you can understand that this is the Green's function for the isolated contact is because there is no matrix or there is no property of the channel which influences this function or this matrix over here. Okay, E is an independent variable denoted energy, HR is the Hamiltonian for the isolated channel, and eta is basically a very small quantity times the identity matrix. So no property of the channel or no property of the contact to channel coupling is basically incorporated in this matrix or in this function over here, and that is why this is the Green's function for the isolated channel. On the other hand, for this case, this sigma is equal to, let me write it here, this is again a matrix, this is equal to tau gr tau dagger. So here this Green's function is the gr is the Green's function for the isolated contact. So the property of the contact is incorporated in the channel, and the property of the contact to device or contact to channel coupling is reflected in this tau matrix. So this property of the contact and property of the contact to channel coupling is incorporated in this matrix or in this operator or in this function G through this matrix sigma here. So this is the Green's function of the channel and not the Green's function for the isolated channel. Okay, so this is an important difference. For the toy example we discussed earlier, we already noted that this matrix sigma was equal to minus T0 e to the power IKA, and S was equal to 2I T0b sine Ka. And in that case, when there was one atom only and one atom coupled to the contact, this tau matrix would become equal to T0, and then S is equal to tau phi r. So this part is basically phi r for the isolated channel, and which is evident because in case of the isolated channel we don't have a propagating wave, we have a standing wave only. So the wave function has the form of a sinusoidal wave function in that case, and a non-propagating or a standing wave in that case. Okay. Now let us try to understand the physical essence of Green's functions. Now we saw that the Green's function for the isolated channel is basically given by Gr equals to EIR minus HR plus I eta inverse. Now if this is expressed in the eigenstate basis, or if this Hamiltonian of the isolated contact, if this is expressed in the eigenspace basis of the contact, in that case the Hamiltonian would just look like an diagonal matrix. So in that case HR basically becomes a diagonal matrix with the eigen energies as the diagonal entries of the matrix, E3 epsilon n, and these entries are all 0. And etc. And therefore this GR is also diagonal in form because this is a diagonal matrix and eta is also a diagonal matrix. Okay, so in this case the Green's function GR simply becomes a diagonal matrix as, and it looks somewhat like this. Zero plus is a very small number. And so on. And so on, etc., etc. Okay. Now this matrix GR, this is basically a matrix which depends on energy. So this is a function of energy. So the energy for a electron wave function is basically related to the frequency, and the frequency is basically the frequency of this eigenstate 1 should basically be given by omega 1 equal to epsilon 1 by h bar. Similarly, the frequency, angular frequency of this eigenstate 2 is given by epsilon 2, the energy of the state 2 divided by h bar, and etc. So this energy is basically related to the frequency of the eigenstate. Now if we want to transform in some other space to represent the same wave function or to represent the same function, we can go to the inverse Fourier space. which is basically the time space. Okay, so when we represent a function in the time domain, the Fourier space is basically the frequency domain, and when we represent a function in the frequency domain, the inverse Fourier space is basically the time domain. So if we basically take the Fourier transform of this function, what do we get? So let us take the inverse Fourier transform of this function. So we then get gr as a function of time as integral minus infinity to plus infinity dE divided by 2 pi h bar e to the power minus I e by h bar t, and g r e dE. Now this can also be the Green's function of the channel. It's not only necessary that it needs to be Green's function of the reservoir, or it can be any other Green's functions. And the thing is that I want to explain what is the essence of Green's function and how it looks like in time domain. Okay, so if we do this integration, we would this matrix gr of t would basically look somewhat like this. So here I have just defined 4 diagonal terms, but there are other terms as well below, the other eigen corresponding to the other eigenstates of the Hamiltonian. And to see that these terms basically result from the Fourier transform of each of these terms here, let us take a particular case to show the direct result that the inverse Fourier transform of this term really gives the exponential function. Not exponential function, but this e to the power I and then the exponential function. It is kind of difficult and involves contour integration. So what I will do here, I will show that the Fourier transform of this term, this entire term over here, this is basically equal to 1 by e minus epsilon 1 plus I0 plus. So if I can do that, I am basically done. I can show that then the inverse Fourier transform of the terms in the energy space is also equal to this term over here. Okay, so let us do that. So my intention is to show that the Fourier transform of minus 1 by h bar theta t e to the power minus 0 plus t e to the power minus I e1 by h bar t is basically equal to 1 by e minus epsilon 1 plus I 0 plus. Okay, so note that this 0 plus here and this 0 plus here is not the same, but might not be the same, but the fact is that these two are really infinitesimally small quantities. Okay, so if I can show that the Fourier transform of this term over here is this term, then it is all proved that the inverse Fourier transform of this term is given by this term over here. Okay, so this is the one element of GR. Okay, now the Fourier transform of this term is basically given by GR11 E. This is equal to integral dt e to the power I e by h bar t, and then this function over here. So minus I divided by h bar theta t e to the power minus 0 plus t e to the power minus I by h bar t, and I basically take this term, entire term, outside. So this integral is from minus infinity to plus infinity. I take this term outside, and then due to this theta t function, which is the unit step function, I have to reduce the limits of the integral from 0 to infinity. Okay, so dt, then e to the power I e by h bar minus epsilon 1 by h bar, and then plus I 0 plus t dt. Okay, so I square is equal to minus 1, so I have put this I in front of this 0 plus over here. Okay, so this is equal to minus I divided by h bar integral from 0 to infinity. Let's just write the result of the integration here. So e to the power I e by h bar minus epsilon 1 by h bar plus I 0 plus t divided by I e by h bar minus epsilon 1 by h bar plus I 0 plus, and then I write the limits outside, so from 0 to infinity. Okay, now at t equal to 0, at t equal to infinity, if I put t equals to infinite here, these two terms give rise to oscillations because there is this I over here. However, this term when multiplied with this I, so this is e to the power minus 0 plus t, okay, and t is equal to infinity. So this effectively becomes 0 at t equal to infinity. At t equal to 0, this exponential term is basically 1. So what do we get here? So we get minus I divided by h bar 0 minus 1 divided by I e by, so I take the h bar outside, so I write it as I by h bar e minus epsilon 1 plus I h bar 0 plus. Okay, so the entire thing then reduces to this this I by h bar and I by h bar cancels, and this minus and this minus sign here cancels out. So we effectively get 1 divided by e minus epsilon 1 plus I h bar 0 plus. Now this h bar 0 plus is also a very small quantity because h bar itself is a small quantity. So we just replace it by 0 plus. So e minus epsilon 1 plus I 0 plus. Okay, so we have proved successfully that the Fourier transform of this term over here is basically equal to this term. Okay, so the inverse Fourier transform of this term must also be equal to this term over here. Okay, now GRT, just as we shown, is I by h bar theta t e to the power minus 0 plus t e to the power minus e to the power minus I epsilon 1 by h bar t. Now let us write a differential equation for this term. So if we differentiate this with respect to time, this is the 1 term over here, If we differentiate with respect to time, we get dgr11t dt del t. So we have two time dependent terms here. One is this theta t and another is this exponential term. So we get minus I divided by h bar del theta t del t e to the power minus 0 plus t e to the power minus I epsilon 1 by h bar t minus I by h bar theta t e to the power minus 0 plus t e to the power minus I epsilon 1 by h bar t multiplied by this now I basically write this entire I by h as 1 by IH bar, and this part is basically delta t. This is the differentiation of the unit step function with respect to time. So this is delta t, and when you have delta t over here, delta t is only non-zero at t equal to 0, so you have to put t equal to 0 in all these arguments here and here. So this basically becomes this entire part basically becomes 1 at t equal to 0. Okay, so IH bar delta t minus, now this part is equal to this Green's function in time domain itself. So I write it as gr11t multiplied by 1 by I h bar I 0 plus minus epsilon 1. Okay, so I take this entire term to the left hand side. And I also multiply this entire equation by IH bar. So we get IH bar here. Sorry, this is epsilon 1 minus I 0 plus gr11t equals to delta t. Okay, now this is the transformation, this is the differential equation in time domain for this 1 element of this Green's function matrix. Now I can do it for all the elements, and I can get a generalized equation which is IH bar gr n t del gr del t, sorry, t dt minus epsilon n, and I basically neglect this term here because it is very small. Okay, now this equation kind of looks familiar. I can also write the matrix format of this equation as IH bar del grt del t minus h grt equals to delta t into IR, where IR is the identity matrix. Okay, and this kind of looks familiar, and it somewhat looks like the Schrodinger's equation. At least this part is equivalent to I h bar del psi del t, or even this part of this equation, del psi del t minus h psi equals to 0. Okay, now this is basically Schrodinger's equation which is of course the equation of motion for a closed system. Remember that Schrodinger's equation is for a closed system. Now what does a closed system means? A closed system basically means a system from which electrons or wave functions cannot leak out of and also cannot leak into. So no electrons can leak out of the system and no electrons can leak into the system. Okay, so that is what a closed system basically means. Now in case of an open system, definitely electrons can leak out of the system and leak into the system, and that is the kind of systems we are interested in electronics engineering or electrical engineering, because in electronics engineering or electrical engineering we are mainly concerned about the current flow through the system, and if current is flowing, this basically means that the electron can either leak out of the system or electrons can also leak into the system. Okay, so whenever we have electrons leaking into the system, we can modify this Schrodinger's equation as I h bar del psi del t minus h psi equals to lambda, where lambda basically denotes the external excitation into the system. Okay, so this part is for a closed system, and then if there is an external excitation, then that external excitation is denoted by some term lambda here. So this entire equation, so this is the Schrodinger's equation for an open system. Now how you write this lambda, that is another question, and there are various lines of thoughts, and it's still under research stage. I would not say still under research stage, but there is a lot of developments, and are still rooms for more developments. Okay, so we'll not go into the details of how you write this lambda here, but I'll just give you an intuitive argument that this lambda here is replaced by delta t, which is kind of an impulse in time or impulse at t equal to 0, and so this Green's function in time domain, this basically denotes the response of a system when your external excitation is an impulse. Okay, for example, here if in this equation, if I would solve for this psi, if I would solve the differential equation and get the form of psi, in that case I would be getting the wave function for a system with Hamiltonian h. H is the kind of internal to the system, it depends upon the system itself. So if I would solve for psi, I would get the wave function, or I would get the response for a system with Hamiltonian h and with an external excitation of lambda. Okay, similarly, if I solve this Green's function here, or if I solve for this matrix here, I would be getting the wave function for the system where the Hamiltonian is given by h, or where the eigen energy is given by nth eigen energy is given by epsilon n, and where the external response is basically delta. Okay. Now let us generalize the concept. What does this term Gmn t? So Gmn is the element of the mth row and nth column of the Green's function matrix, and what does it indicate? So let us assume that the Green's function is written in a spatial basis. So what does this term denote, or what does this term give us? This depends on what basis we are choosing. Let us say that we have chosen a space basis. So we have expressed our wave function in terms of the value of the wave function at different points in space, which is the space basis, and we have this points labeled as, let us say, 1 2 3 4 and m, and then after some n, and then blah blah. Sorry, this should be n. So this term, if we denote the wave function in space basis, this term would basically mean that if I give a impulse at the nth point, so I give a impulse of delta t at nth point, how would be the response at the mth point? So I give an impulse at the nth point over here, and I measure the response or the time response at the nth point. Okay, so this term exactly gives us this time response of the mth point, or the wave function response, the temporal response of the wave function at the mth point when this impulse is applied at the nth point over here. Okay, now we might say that no, we will not use a space basis, but we would use a wave function basis, okay, or the eigenspace basis, let us say. So in that case, our basis is consists of, so this is the space basis. Let us say that we would not use the space basis, but we want to use the eigenspace basis, which is also a valid choice. And we say that our basis functions are basically psi 1, psi 2, psi 3, etc., where these are basically the eigenstates of the Hamiltonian. Okay, now in this case, what does this Green's function Gmn indicate? So there is psi m and psi n as well. So let me write it here, psi m, psi n. So what does this Green's function mn t in that case indicate? So this indicates that we apply an impulse of this psi n over here. Okay, we apply this impulse of psi n. So if psi n was not present in the system earlier, we are now suddenly starting or applying an impulse of psi n, and we are measuring the temporal dynamics or temporal behavior of psi, this wave function psi m, and this response is exactly given by this term Gmn t. Okay, so note that although things are complicated here, note that we started with Schrodinger's equation for a closed system, and we gradually added a few terms in that equation, and we ultimately got if the excitation response of the system as a whole. That is, if we apply the excitation at a given arbitrary point within the system, what is the response or what is the temporal response of the wave function at other points in the system, or if we apply an excitation for a component of the wave function, in that case what is the temporal behavior at the other components of the wave function. Okay, or it depends on which basis you choose basically. So this is what the physical essence of Green's function is. And let me just tell you that Green's function is not a concept which is only used in transport. So Green's function is a very generic concept which has been used in various areas of mathematics and physics, as well as in classical physics. And when we say Green's function, it simply means that what is the solution to an equation when the excitation is an impulse excitation. Okay, well, that is a general way or the layman's way to explain. I would not say that this is the correct language which I have used here, but since I think most of you are students from engineering background, just satisfy yourself with this much. And let me just right now just know this, that Green's function has a much broader scope of application rather than only in electronics or in transport physics. Okay, so let us do up to here today. Thank you everyone.